William Valentine Professor of Physics at Caltech, and he's the director of the Institute of Quantum Information and Matter. He did his PhD at the University of Rochester with Professor Mandel, not Professor Boyd, but Professor Mandel. He's done many innovative things in research. First, teleportation of quantum states, quantum logic gates, development of the first single atom laser are to name just three. Jeff is a fellow of the American Association for the Advancement of Science, the American Physical Society, the Optical Society of America, and the National Academy of Sciences. He's won many awards, and I'll only mention a few again. He's won the Einstein Prize from the laser science, for laser science from the Society of Optical and Quantum Electronics, the Michelson Medal from the Franklin Institute, the Max Born Award from the OSA, and the Herbert Walter Award from the American Physical Society. So it's great to have Jeff, and welcome.
So thank the organizers, Paul and the much maligned Bob. I turned 60 once, apropos to Bob's 70. And a friend came up to me and said, "Wow, that's great. You don't look a day over 70. It really is an honor for me to be here to celebrate the life of these two amazing scientists. When they were young and did graphics not nearly as nice as we can do in the modern era, but all the way to later in life. I had the amazing good fortune to meet and interact with both of them. I certainly don't know the whole path, but the best I could recommend to you is to try to read this book if you haven't. It really tells in a marvelous way insight into the character of Schawlow-Townes, but also his brother-in-law. And it's just a great story. So what I want to tell you about today is a new way for atoms and photons to interact. And this is out of some PhD cartoon, if you know that. I didn't, but my graduate students did. My daughters never really appreciated my scientific life until when this appeared on the internet. One of their biology friends who was in graduate school called and said, "Wow, your dad was on PhD comics." And all of a sudden, to my teenage daughters, I'm elevated to, well, maybe we can talk to him. Anyway, there's an amazing set of people who've contributed to the advances and that we're making, both technically and scientifically, and I'll try to point that out as we go. So, the broad theme of what I'm trying to do is find a new way for atoms and photons to interact. And I think because we need it. We're in a wonderful era of quantum information science, both for quantum computing and quantum communication, but also for applications we won't really understand for years to come. There are new things discovered on all kinds of fronts. A frontier of research now is how do black holes work? And some of the best contributions now have come from quantum information, quantum error correction. So it's not going to be easy. It's a grand challenge. So here we are. But what I want to do is try to build up quantum system for diverse applications. I need what I call quantum Lego blocks that each work really well. I want to use atoms and photons, so there's something inside of here, material systems, and in the electromagnetic field, in the optical domain. And I want to build things out of that. And if I can do that, I'm confident that we'll find things in the lab of a sort that haven't existed, at least in the natural realm that humans have explored. For example, there are complicated things about networks like this in the quantum realm to get entangled and so on. That's going to be important to learn about in how to characterize this and measure all this entanglement stuff. But what I'm really interested in is, look, when a superconductor was discovered 100 years ago, nobody had to tell them about BCS, which came 50 years later. You just put an ohm meter and boom, cool it off. You know, anybody's got enough sense to buy a tuxedo and go to Stockholm. So I want physical systems that are surprising. And for that, we need, I believe firmly, a different kind of way for atoms and photons to interact than we've had in the past. There are, I think, important scientific applications, technology I won't forecast, but important scientific applications. So that's the broad goal. Traditionally, the quantum interactions of atoms and light, and I'll just restrict myself to atoms, there are all kinds of other wonderful systems, quantum dots and superconducting devices, have been of the ilk to get into a domain where one photon interacts strongly with one atom and conversely. Cavity quantum electrodynamics has been important. You put high reflectivity mirrors, the light can bounce back and forth, and you can have strong interactions. One isn't enough. Well, send light through a dense atomic ensemble in the beginning of either cold atoms or hot vapors, and one can do things like make a quantum memory. And in this case, it's the figure of merit is just optical depth. In this case, it's essentially optical depth associated with all these multi-passes of a single atom. Or why not just use one atom and focus the light very, very tightly to have a large cross-section? That's a really hard problem. It seems easy. The best progress has been about 20% absorption for one atom. And I'll show you how to do a lot better than that. Gerd Loix has been working a good part of his adult life to figure out how to do this in a more clever way to really push up the interaction cross-section. And what I want to tell you is these traditional things are really exciting. They have a great future, but they're just not enough for what I want to try to accomplish in my lifetime. We have to find a better way to have atoms and photons interact. And so I'm going to tell you about that, but I also want to tell you that that's easier said than done. So look, this cavity QED, that seems kind of okay. Put an atom between two mirrors, the light can bounce back and forth, put it inside of one of these cavities, and let's just ask how well that's done inside of one of these nodes. This is the number of photons it takes in the cavity to saturate the atom, to change the transmission so it's not absorbing anymore as much. The transmission doubles versus time in my life. And you can see I started up just when I became a faculty member a long time ago. And these are measurements made with cavities like this. We got to here, and we're going to run out of gas, but in collaboration with Kerry Valhalla, we learned how to use microfabricated whispering gallery mode cavities that were pioneered in a more microscopic scale by Vladimir Brzezinski, and trap an atom there. And by that avenue, we've done okay. From when I started in the early 80s till 2010, we pushed this critical photon number down 1 billion times. So when I say I want to do better than that, to a limit here where the critical photon number is 10⁻⁵, it's not to be taken, oh yeah, and I'll do it in the next funding cycle. You don't put that as a milestone. You put that as kind of a life goal. This is what's the right technical, scientific way to go about that. So in that context, the right way that I decided, and again, it's not going to be easy. This is a kind of lifetime endeavor, not something that you just think you get done on the weekend, and it's going to be hard. But the idea is to harness the $1 trillion that's been invested in nanofabrication. And because by now these materials, dielectrics, low-loss dielectrics, which can have very low input and output losses and efficient transport, cavities of 10 to the 7th, 10 to the 8th quality factors. Here's an example of them. This is just two parallel beams. They're going to be tiny things that can have a solution to the Helmholtz equation where the light propagates forever, absent defects. Here's one I'll talk quite a bit about, this so-called alligator. It's a modulated dielectric. This is silicon nitride, and everything else is vacuum. These two parallel beams I'll tell you about. This is an advanced version of that. In what way is it advanced? It's advanced to allow this dialogue between atoms and photons to be even stronger. We can do these things in quasi-one-dimensional structures, two-dimensional structures. But at the end of the day, everything I have on here, this is just a cartoon. These we've really made. These are linear dielectrics. I'm not after these really high field strengths that some crazier people are after all their life to melt and blow up things. I want, linear dielectrics. How do I make them quantum? I functionalize them by putting each of these little spheres, we'll talk a lot about, are single atoms. And single atom is about the biggest nonlinearity you can get for quantum light. It's in the ground state or the excited state. If it's in the excited state, it can't interact with another photon. If it's a ground state, it can. So it's really 100%. And so I'd like to get that. And if you have things like that, immediately, if you try to send photons through it, the photons are caught in some kind of quantum pinball between one and the other atom. If you try to send a couple of photons down, two photons that try to interact with that atom can't. It's just a hardcore interaction, one and only one. So simple things on small scales can we build up to do a new kind of science. And I want to convince you that we can. First, I'll tell you a little bit about this alligator. It's named after this creature. Not too many in Canada. But alligator, this is just silicon nitride. There's a vacuum gap of 250 nanometers. It's engineered specifically for atom-light interactions. And as a physicist, there are some colleagues, if I told I'm engineering things, they would go, oh God, that's dirty. But no, engineering to do new kinds of physics. And the physics I want to tell you about is if we had one atom inside of there for this device, which we've already made and done experiments with, if we put the atom in the excited state, most of the light would go into the guided mode and a little bit into free space. And the key figure of merit is how much is going into this one-dimensional waveguide compared into free space. And you can just think of this number as being Einstein A coefficient, order of magnitude. That's the rate in free space, which in the optical domain for dipole-allowed transitions are rates of megahertz. So if you have that and you send light down this little waveguide, it's a guided mode, it's a solution to the Helmholtz equation, it's got some kind of funny shape and polarization, but it's orthogonal to the other guided mode. If this is what we've achieved in the lab, so a photon propagates along here and one atom can have a 90% reflection coefficient. Essentially, all the light is reflected. The transmission for this device, which we already have in the lab, is 1%. We're going to build devices. We've built devices, but not yet put atoms in them, where the transmission will be e to the minus 8. The optical depth of one atom is 8. That's important. One needs to be a big number. What can we do with that? Well, I'll tell you about this a little bit. The critical number I just showed you on that graph, I said that 2010 and 11, I didn't know how to keep going. How do we keep pushing that to new frontiers, not by factors of 20%, but by 2 orders of magnitude relative to what I showed you before, and I'll show you that that's been done in an experiment in Harvard. We can engineer atom-photon interactions. In free space, it's just the rule that you know, that's bounded by kind of Fermi's golden rule stuff. So we can engineer things so that if we have two different frequencies, those could be atomic transitions that are going to be doing two different things, like interacting with photons and one frequency to hold the atom. In free space, those necessarily have different length scales. So you're holding the atoms, all these atoms, is mixed up with having them interact. They're out of phase. So in a photonic crystal, if this is K and this is omega, this is a photonic crystal. It's a modulated dielectric constant. You can have two frequencies which have the same length scale. That's really powerful for doing atom-photon interactions. Furthermore, if you go to this band edge, as we heard this morning, there's a really high density of states. It's a Van Hove singularity. In perturbation theory, the density of states and this emission rate diverges. So that's not a 10% effect if we can really harness it. So if we put not one atom, but lots of atoms, then the question is how are they going to interact with each other, bouncing photons around? But we instantly get into a world for either atom-atom interactions or photon-photon interactions that lets us do, I think, a new regime for quantum many-body physics. Okay, so just to show the qualitative character of this, if you take this experiment, I told you this is what I didn't show you that, I showed that. This is an experiment by Jeff Thompson as a graduate student in the group of Vladimir Vulatek Misha Lukin at Harvard, done 5 years ago. And what they were able to do is trap an atom in some kind of a little photonic crystal which has a localized mode, a defect mode, which makes a new version of an optical cavity in a low-loss dielectric. And they were able to take this critical photon number and push it down 2 orders of magnitude. That's great. That's a new opportunity for cavity QED to go on 2 orders of magnitude. On the other hand, I told you that in this alligator structure, one atom in the waveguide, so that's the atom that's going to be the cavity QED atom, that atom can make big reflectivity. So I'll make my reflectors not macroscopic dielectrics. I'll make them just an atom. Atoms are inherently, it's the internal degrees of freedom of the atom. They're inherently quantum mechanical, so I don't actually need that atom. That's my cavity QED system. Furthermore, the mirrors are quantum mechanical, and they have not just internal degree of freedom, like being excited and decaying, they have a center of mass degree of freedom. So the cavity is quantum mechanical and will be transported along together with whatever the atom and photon internal degrees of freedom are doing. That's qualitatively different. That's a kind of physics that people hadn't really thought about at all. So that's the character of what this wild goose chase is about. Okay. Let's just take this one. There are other kinds of photonic crystal designs, modulated dielectrics, but if I have this modulation in a simple story, there's going to be a wave vector for propagating along here, and then a frequency, and this is a dispersion relation, and then there's this photonic band gap. And let's just look if the atomic frequency is in this domain, it's in a propagating regime. That means that the fields that propagate are roughly plane wave. They are different, and I'll talk about that in a minute, but they're propagating modes going either way. And if we put an atom in there, then it can emit. And if there's another atom in there, it can absorb and send the photon back. And in that case, that interaction would be described by just this gamma 1D, the likelihood to emit into the waveguide, times some function that says, okay, what is the interaction for 2 atoms at positions zi, zj? And this is just that one atom goes to the ground state, emits the photon, and the other one absorbs it, and then that can just go back and forth and oscillate at this rate, gamma 1d. That's the basic rate of this whole story. And so you can have coherent atom-atom interactions, but because these guys are connected to this channel, this guided mode, this atom could incide just to emit off to infinity. So this is what's called a mastery equation. This is the Lindblad loss term. So there's collective dissipation where not just this atom, but both atoms can do things together. If I put a bunch of atoms there, then they can all do this, and they can all do that. And so that means things can get kind of complicated with the photons bouncing back and forth. This story has this evil character, which is emit to free space. It's not completely a 1D system. So the ratio of this to this coefficient is the figure of merit. So we've got to find systems where this gets bigger and bigger and bigger, both by suppressing this relative to vacuum. You can't do that in normal atomic physics. Turn this off a factor of 100, and turn this up a factor of 100. And now we're talking. And that's, I think, sensible in the future. So these are the 2 kinds of processes. Because this has this functional form, it's actually possible to space the atoms, if they're spaced the way I showed you, lined up with the teeth, say. This can be turned off, strictly 0. And then we just have this collective dissipation. But why does anybody who want to do coherent quantum information, coherent optical processes, want to use dissipation? Because dissipation can be a friend, a really good friend. Let me tell you one example. You might know that one of the protocols for building quantum networks is to put atoms in cavities and have them transfer their internal quantum state into a photon to send somewhere else, or to send half a photon somewhere else and thereby entangle remote locations. You can do all of that on a bus like this. This is just the waveguide I was telling you about. And here's an atom, and just by fixing its position right, you can transfer its quantum state information somewhere else, or entangle that atom with some other atom. And that's described in this paper. And that's all done by a dissipative process. The Hamiltonian I wrote for the coherent spin-spin interaction is strictly 0. Here's another example. Here's a nanophotonic waveguide. I don't want to just take one photon, half a photon. I want to make arbitrary quantum states where spin up would be, say, an atomic excited state, spin down would be the ground state, and I want to make for n atoms, here 6, arbitrary quantum states. Well, that's useful. That's the kind of thing a quantum computer does. But I'm interested in atoms and photons, so having made that state with very small errors, I want to launch that state out into the world. And if somebody's out there and wants to send me something back, I can map back and forth. And the best, this is all done in a world of dissipation, dominated in the channel. The error you make, 1 minus the fidelity, is just given by this figure of merit. That's good, times 1 over n. That's the best anybody's been able to do. This is a work by Gonzalez Tudela and Ignacio Sirac's group. And the thing you get that you don't normally get by this setting is this n. This is the best scaling in a number of settings, and now we get this in. So that's good. But we want to do better. And in work by Derek Chain's group, led by Anna Seno, this is theory. We want to take, and now let's just concentrate on a quantum memory which takes a photon and sends it back out, or a half a photon, stores it, sends it back out, entangled states of the optical field. How well can we do this little story of a quantum state comes out, it could be entangled with something somewhere else, and then comes back in. What's the error we have to make? And this is the error. It's called the infidelity. It's just 1 minus the fidelity. And if we look at this, this is the best that people have been able to do before in any setting, cavity QED, these memories I showed you, which has this 1 over n kind of dependent and some ratio like that. This is just going to be the optical depth in the ensembles I showed you. And now what you see is this line is exponential. The error is, this is logarithmic, is exponentially suppressed. So it looks like that. Again, this work by Ana Seno Garcia. And that just hasn't existed in optical physics. This is one of 2 exponentials I want to tell you about that gets us away from 10, 20% improvements. If you do that often enough, you can get Moore's law, but never mind. I don't have that much money. So exponential improvement, exponential suppression of errors. And the only other place to find that in an easy way is in a superconductor. A superconductor has exponentially suppressed absorption if you're below the band gap of the superconductor. So we need those kind of things in atomic physics, and this is an example. Okay, here's another example that's a little unexpected. It's chiral quantum optics. Now we're going to talk about the polarization of these guided modes. So this is a dielectric. I'm sorry I didn't draw this very well. This is a structure that was designed by my former graduate student, Su-Ping Yu. So the dielectric is this. This is a piece of dielectric all inside here. This is vacuum outside. And now what's shown is that as the light propagates along like this, then the light is circularly polarized. And it's a property of these little dielectrics that you can have light which is circularly polarized, but it's polarized not transverse to the propagation direction, but along the polar. So if you just look at this arrow, it's circularly polarized like that. Almost perfectly circularly polarized. For the thing running this way, depending on how you want to do it, this is right hand and the other way left hand. This is how well is the light polarized in this device. You can see by the arrows, it's maybe hard to track. In these little gaps, it's almost 100% right sigma plus, and down here sigma minus. That's good. And we got that by doing nanophotonics kind of like the alligator, but we just got rid of half the alligator. We broke the lateral symmetry. And so what's the interest in that? Well, that's something that this group of people, Peter Lodel and Arnold Roshenbuhl, principal among them, said, hey, that's a linear dielectric. It evades time reversal invariance. But you can break that if you just put atoms in the right place. These atoms have say F equals 0 ground state and 1 excited state, electronic state. So this makes sigma plus, sigma minus, and delta M equals to 0 linear. But if these atoms are there and the light's propagating like that, that's the only transition you can drive. Furthermore, if the atom is excited by this incoming photon, say, it can only emit to the right. There's none of this plus minus stuff. By the same token, if I put an atom is here, and light comes this way, it can't interact with it. That's because sigma plus is down here. So K going this way, this atom would not interact with it. So it explicitly breaks time reversal invariance. The dielectrics that I showed you, they have interesting properties, a lot of things we saw for the way light propagates, but it's all time reversal invariant. This breaks time reversal. And that means it's possible to make some fairly exotic quantum phases out of this, and I'll show you one of them. This is the best example that's come out of this, but only in a year's time. It's a whole new field that's been created by Lucan Zoller and these two young people led by Hans Pichler. This is to take an atom and to have it be in one of these waveguides where the emission to the right or to the left can be controlled, can be engineered. For example, in one extreme, the atom only emits to the right, or in another, only to the left. But let's just tune it to engineer it. This atom is going to go up in the excited state, and say it emits a blue photon going left, put a mirror there, it comes back, and then goes out. Let me unwrap this mirror to show it like this. In this way, the atoms in this is only going to emit to the left. And then we're going to go down and put a mirror, and then it comes back. But we're pulsing this atom, exciting it to emit, over and over at just this period tau. So the light goes down, comes back, and when this photon gets there, it's going to interact with the next one being generated. This photon and that photon interacted. This one's gone that far, but at one cycle before, this one was being created when the other one went by. And atoms don't like that. So one electron can only do one thing or the other. So these two photons become entangled. So if you take this linear chain and just wrap it around the cylinder, the red things are going around like this. Early time's back here, and then later time up here, or the other way around. And so if you wrap that on a cylinder, then this photon was created at the same time was created at the same time that one went by. And so you see on the cylinder that they actually are connected. And that kind of simple takes 1D and turns it into 2D of these photons wrapped around, can create the light that comes out of here. It's just a chain of photons. You can think of a chain of qubits in a quantum computer, and then you're going to run them through a circuit. That's already been done. That chain of photons is in what's called a 2D cluster state. And that's a universal resource for quantum computation. So what does your quantum computer look like? If one could make that work, that's the whole computer. You make 1 million photons, and you've done 1 million operations. And it's really a universal quantum resource. And it's as simple as could be. So there are really new ideas which I think are qualitatively important for things like quantum information science coming out of this. Okay, let's do something stupid. Let's put the atom transition frequency in the band gap. Well, then what happens? Well, when the atom tries to emit in the band gap, in a photonic crystal like this, the light is exponentially localized with a localization link that depends on where you are in the band gap. So an atom emits again. It really can't emit, the light doesn't propagate. And so again, we have the same Hamiltonian, a second atom next door can interact. We have the same Hamiltonian I've been showing you, but this part now is strictly 0. That's because in infinite structure, there are no guided modes propagating. They're exponentially localized. So this little thing was first described by Sadib John and Gershon Krushitsky in 1990, and it's a kind of a bound state of a photon around the atom. But now if there's another atom around, the photons can hop. So it's like spin-spin interactions again. This one can go over to there. If you have a lot of atoms in there, then you're in the business of quantum many-body physics. Again, the figure of merit is just that. So that's the Hamiltonian we're dealing with. It's got some kind of interaction energy and some kind of a length, this function. And this is just atoms going up and down, spin flipping, if you will, from excited to ground states. This thing can be completely engineered to be of arbitrary form. Never mind this kind of usual form, but colleagues and I have written papers about how you can make whatever you want there. Furthermore, so that's spin-spin physics, quantum magnetism. Furthermore, if you look at this thing and say, well, it's a function of space, if you just think this is the energy of the system and you take a derivative of this with respect to one of the z's, then it's a force. So all of these atoms are going to be held somehow, but they're going to be, when they do one of these things, spin flip, send photons, there's going to be forces on them. And those forces can lead to new quantum states of matter, new quantum phases of a sort that haven't existed before. This is the block mode of a photonic crystal in the band gap. This is the alligator they consider, Derek Chang's group. And this is just the spin-spin interaction that I was telling you about, this J. And so the atoms, these two atoms, say if they're like this, would want to attract each other. And then two other atoms, this atom could be attracted over here. So you have to ask, okay, what happens? And what happens, this is a phase diagram that has to do just with, this is just this J coupling, and this is like a magnetic field, which can be applied with an external laser. And they've predicted, they haven't filled out the whole phase diagram, but intersteam quantum phases, this is just what's called the Neal phase, which is just a product of spin up, spin down, so it's not entangled. But this is this phase I want to concentrate on. It's called a dimerized triplet. So the two atoms want to attract each other, but they're both bound. The only way they can attract each other is to move and become entangled. So you get a singlet state, but not a singlet state in the normal way, where it would be this plus that entangled. It's this plus that entangled with that motion. So it's a really novel phase, and it's the first really serious attempt to look at what could we do if only we had these kind of resources. Another one, which I won't spend very long on, is just to say this is again from James Douglas in Derek Chang's group and Ephraim Shamoun with Gershon Krushinsky, is to show this is a pair of photons propagating. And now what you see, propagating along next to each other, but offset in distance. And what you see is the two photons are that far apart, and now they're closer, and now they're farther. So in the frame in which they're moving, the photons, which are localized somewhere along one of these 1D chains, are actually oscillating back and forth. It's a diatomic made out of photons. Where does the force come from? Where does the potential come from? Well, you may know there's a formal analogy between Helmholtz equation and Schrödinger equation. And if you have an increased dielectric constant, then that's an attractive force. So the dielectric, this photon excites a little bit of this underlying lattice. It's this 1D lattice. And so the dielectric now are these atoms which interact with these J spin interactions, which is then transferred to the photons. So you can make, maybe one day, here's a 1D chain in my dream where we have not two. What I showed you up here is just two photons with a spring as they oscillate. It is a long linear chain of photons that are bound or repulsed. The point of this in a broader context is I'll mention a little bit later on, is you're used to thinking about the dielectric constant of a material to be something that maybe is chi1 and then chi2, chi3, and so you turn up the power and you can have nonlinear things. This is a dielectric. When one photon propagates, it's got a certain dielectric constant. When two photons propagate, it's completely different. There are actually examples where you have a material with a band gap, the photonic crystal, and one photon propagating can renormalize the whole band structure of the dielectric, albeit over a narrow frequency range, but that's kind of amazing. In 2 dimensions, all of this story works. This is a paper where a lot of it got worked out. We just changed 1D to 2D. In 1D, we have a guided mode going one way or the other. In 2D, we have complicated guided modes that have to do with the underlying symmetry of the lattice. And this is what a band structure looks like for a square lattice like that. And the important thing to say is there is a place where we can trap atoms. We need optical tweezers, if you will, inside each of these to hold the atom. And a place where this is this, in a 2D structure like the Van Hove singularity, where the band goes, the dispersion relation goes flat, so the group velocity goes to infinity, goes to 0, the density of state diverges. And in 2D, I won't go through it, but there's a richer set of things one can do. The physics, many-body physics. The atoms mediate interactions between photons, either propagating photons or in the band gap. Photons mediate interactions between the atoms. That's what I told you in the first part. But it's also true that the previous view graph, photons can interact now mediated by the underlying lattice of atoms. And in that case, you might imagine, could you make a benzene molecule if you had 6-fold symmetry in a lattice that's just propagating along oscillating? That'd be kind of okay. Okay, in the lab, Suping Yu, Juan Munez, with the design and the actual fabrication. This is a square lattice. We've made that kind of structure here, the dispersion relations. This is a hexagonal honeycomb lattice, hexagonal. This is the dispersion relation, which has some interesting properties. And the goal is to try to do that, to functionalize these dielectrics by putting atoms inside them. There's lots of interesting properties from 2 relative to going to 2 dimensions. If you just put a dipole, I left the dipole out. If you just put a dipole, where's my dipole? Inside of here, then the radiation properties can be very different depending on the frequency you choose the atom is the dipole drive, where you are in the band. So you can make roughly the equivalent of these chiral materials, where the things only want to go in one way or the other. If you have your excitation not inside the band gap. On the other hand, if you want to put your excitation inside the band gap, for example, with that, here's this hexagonal lattice, then this is what one atom radiates. Well, it can't radiate. This is the little triangle I showed you in 1 dimension for the radiation, and it's got a rich symmetry. And if you put atoms inside of here, you can functionalize this to be very, very quantum. For example, up here, there's a K point, which is well known in nanophotonics, in a structure like that has a special property. It's just like in graphene. And if you put atoms in a lattice like that, they make, again, this hardcore interactions for photons. So you make it a highly quantum and nonlinear system. Okay, so that's the idea. Let's go in the lab for a few minutes. This is the alligator. This is the structure that supports it. Here's a chip that goes in the vacuum chamber. You can't quite see them by eye, but every one of these little tabs hooks up to a device and the light goes through it. That's the alligator I've been telling you about. We had to do all kinds of things, learn about nanophotonics. My group didn't know anything about that. And then we end up with this. We get into here, we got an impedance match, and then there it goes. That's the alligator. 150 unit cells, they're all counting. And it comes out. And we've learned to do all of that with some high efficiency. We've learned to do just about that. This is an exaggeration. 4, we've learned to trap 3 atoms. And I'll talk about that in just a minute. So that is the big roadblock in the story. So we know pretty well how to do these. This is the band structure of that. So it's K and omega, and there are TM modes and TE modes. And what we do is just the picture I showed you, you take that and put it in a numerical solver, and you can find the band structure. So this is not calculated. It's numerically evaluated for a real photonic crystal. And we've measured it, and the data points just overlie these lines. So we know what we're doing. The nanophotonics has advanced to the point where, yeah, we can do real atomic physics. The example I'll give you just at the moment is, what if we have an atomic frequency here in the propagating band? We have an atom in here, its frequency is like that. And then we move the atomic frequency so it's in the band gap. Well, we can't do that, but we can heat the device and move this whole thing up and down by 300 gigahertz or so and ask what happens. And what happens is this. These are measurements we make of light goes through and transmission, so they're transport measurements, versus detuning relative to the band edge. So out here we're in free space, and when you're in free space, this is just this enhanced decay. If there's 3 atoms, then this gamma 1D gets enhanced 3 times. So you see this nice collective enhancement. That's super radiance, and then as you go into the band gap, these excited atoms have nowhere to radiate. So this is actually exponentially suppressed as you go into the band gap. On the other hand, if you look at this spin-spin interaction, the Hamiltonian part of that has some kind of funny shape in the propagating domain, and then when you go in here, it's fine and dandy with some error. But this should just go on and on and on. These points get enhanced because there's this pileup, this Van Hove singularity of modes here. So that's better than free space. Furthermore, this imaginary part of the Green's functions for all the interactions is exponentially suppressed. That's the second exponential. So we're in an exponential twice now in terms of atoms and photons interacting in these structures. Okay, that was published 2 years ago, led by Jonathan Hood. Okay, the grand challenge in this whole world is how do I do what I so easy in PowerPoint? How do we get high density lattices? Well, let's have single atoms. Let's just start with optical tweezers. I would be really happy to have an atom there and an atom there, excite this one and have it communicate with that one back and forth, and as a function of distance, measure all this stuff I've been telling you about. Kind of proof of principle for the individual. All of that stuff that's in those 2, Hamiltonian and Lindblad, are just real and imaginary parts of a Green's function. Let's go measure them. What about in a 2-dimensional structure like this hexagonal graphene-like lattice? What if we could trap atoms like that and just move them all around and measure these 2-point Green's function? That'd be great. So that's our kind of modest goal in this thing. The emission in 2 dimensions has very large anisotropies. This is the dipole orientation I left off in the other one. That would really be fun to explore how atoms really work in these structures. But in my view, we don't know enough yet to get up to this kind of 150 atoms in one of these lattices. Nonetheless, we've made some technical improvements in both the way we couple into these devices and how we hold them. We've got this nanophotonics, and it just doesn't want to live inside the typical AMO vacuum chamber of cold atoms, which is kind of this big. That we've now got it down to this scale of a few centimeter cubed. And that's where we're working on it. A lot of this I need to thank, I learned from the big advance that let us do this. How do you fixture these kind of things? I learned from a conversation with John Hall and Junior at Gilla. So, but I don't think that's not in the short term. It's years and years still. I'm looking for a push the button and it's full, you know? So you go to the store, you buy eggs, you know, it's full. So how do we do that for 1D and that for 2D? And how do we do it in a way which is people who, if you're in atomic physics, you see me do that so many times, you say, throw the bum out. You know, how do we really do that? So let me tell you how I want to do that in the last little bit. We want to put the atoms in a guided mode optical trap. There are modes that go this way, they go that way, they have block modes, they can make standing waves, they make a fort. And so this is a cross section, the alligator's coming out of the page, and this is the kind of trap that we want to make. And that's where we want to put the atom. This is the dielectric. This white stuff is the divergence of Casimir-Poldr to minus infinity. This is a dangerous place for an atom. So we want to confine it and not have it touch these surfaces. So if you look at cuts in these potentials, this cut is like this. This cut is into the page. You can't really see it. These are fabulously small traps, 50 nanometers or something. This is the trap which goes this way. And it's a beautiful trap associate with the light I put in a guided mode. But then I have to put Casimir-Poulter in the story, and then you see that it really gets shallow. Nonetheless, the trapping frequencies are really quite respectable for optical traps. A megahertz, 600 kilohertz, 200 kilohertz. So that's where we're aiming, but it's a really tiny place compared to what has been done traditionally. So here's how we want to do it, a little atomic physics. Put an atom in one of its hyperfine states in an optical lattice. It's just two beams like that. Put it in one of the hyperfine levels, and then let this lattice move. It's just two lasers going like that, and change the frequency of one, and this atom then moves over, and this is meant to be the guided mode trap I just showed you, which is a guided mode trap for F equals 4, ground state in cesium, 9 gigahertz away. And when this comes through, it's not going to stop, it's just going to be running along. When this comes through, we're going to know the atom's there. I'll tell you how that happens in a minute. And we're going to trigger on, with about 50 nanometer resolution, knowing the atom's there, a beam that goes to some excited state. The atom can decay back here, or it can decay there. And if it decays there, it's absolutely trapped, because this red is a lot deeper than that blue. So it's so small, the transit times are microsecond, and traditional cooling just doesn't work. We got to get rid of whatever energy that the atom's coming into the device in a microsecond. You just can't do it. So this is based on a scheme that Mark Razin's group came up with at the University of Texas at Austin. The lattice, of course, keeps moving. So in my dream, here's the lattice. In my nightmare, here's the lattice. We're going to move it through here. Boom, boom, boom. With some probability in each lattice pancake, this comes, the 1D lattice is moving like that. I'll call that a pancake. It fills. And look at a cross-section. This is the alligator. These are the trapping sites. And boom, 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 it fills. So the estimate is in a millisecond, we could have 200 atoms trapped. And they will trap only one in a cell because of something called atom blockade, which I won't get into. Boom, push a button. A millisecond later, it's full. Okay, let's try to make that story a little more real. We already tried that, it didn't work 2 years ago. So what have we been doing? Getting more and more into the dirty plumbing of details of the experiment in physics. So let's just run a lattice through this device. It's held in free space in a vacuum, and we run through it. And we have a probing beam going through with high efficiency so we can measure absorption. So every time this lattice goes through, the absorption drops. The optical depth goes up and the transmission, the absorption goes up and the transmission goes down. What are these red things? At the same time, the lattice itself scatters into this guided mode. Only a part in 10 to the 8. That's not important. The important thing is we can measure, it's about nanowatt. It's gigantic compared to the probe beam, which is picowatt. We've got markers for when the lattice is moving. So we can just shift all of these down by 1 lattice times, 2 lattice times, and so on, and fold back. And that dip, as a function of the frequency we're sending in, tells us about this internal environment where the atoms are. And I'll call that, in the next few graphs, what we call a clock spectrum. So this is a clock spectrum. Let's get those off. As a function of time, a little over a microsecond. That's the time to move through 200 nanometer thick silicon nitride, and detuning of the laser. Just tune the laser somewhere and let the atoms run through. Do it a few times where you fold this back and you get a graph like that. And then use another detuning and so on. It doesn't take long, 5 minutes to build that picture. Just look at cuts at it and you'll understand it better. It's just it's a transmission spectrum. Depends on the frequency and the time. Crucially, the time as the atoms come in. Here's the other cut. You can fit these. You can fit where the line center is. Those are AC Stark shifts, Casimir-Poulter shifts. You can fit the line width, and from that you can extract these rates I was telling you about earlier. This emission into the waveguide, these spin-spin interactions, AC Stark shifts, and Casimir-Poulter. Okay, so we know how to do that. We have 2 tools at hand. We can measure the probe through there. We can send the probe into the alligator as either transverse, which is more or less perpendicular to the surface, or transverse magnetic, or transverse electric, which is like this. One of them's allopates like that. And this one mostly knows about this top and bottom surface. This one mostly knows about the edges, both on the outside and inside. And that's where we're interested in getting the atoms. So how does this transport really work? And let's be serious about it. And for that, I've gone to my Hollywood, it's good it's in LA. We've done numerical simulations. That's the basis of trying to understand what's going on down there so we can finally trap these atoms. This is the red moving lattice. It's just two beams like that, but they go by this nanoscopic structure, so there's just tremendous amounts of diffraction that causes the atoms to move. And here's how they end up moving. This is Casimir polder around the device. This is the moving lattice. Notice how the lattice is distorted because of the diffraction. But then here come the atoms. Crash on the surfaces. Oops. Oh my God, what a terrible movie. Oh, I'm not good. Lucas, don't tell me. Okay, there we go. So this is the classical particles, but nonetheless, this is all done with the help of Amazon Cloud. So the only force is Casimir polder and the lattice, which however is diffracted as a function of time. And hopefully you can see that, there's a lot of crashes, there's stuff going on the side, but atoms do make it through. And that's happy. On the other hand, now, let's take a red detuned lattice that has its own forces because it's diffracted as it goes in, the atoms are trapped. And now we're going to put in a guided mode of much higher power. Than the probe. It's going to be tens of microwatts and Casimir polder. And now let's see what happens. This is Casimir polder. This is the TM guided mode, which is strong on the surfaces. You can't even see the lattice because this is strong. And now here come the monster creatures from Mars. And this stays okay. However, these guys come in and just fly back very close. That's important when they come. They run up this repulsive blue and then they fly. Okay, so we know the trajectories. If you know where the atoms are at every moment in the vicinity of this thing, then you can do a simulation called matrix transfer for one-dimensional transport of light, and you can come up with a spectrum. So this is the measured set of clock spectra. This is with no external, nothing but the lattice of Casimir polder. This is as we turn up that incoming start beam from 0 to 70 microwatts. And what you see is that's not so interesting, and then you begin to see this kind of stuff. It gets more complicated. This is the color code for the transmission. So that's what we can measure. And then we can do these simulations all the way from the transport of the atoms, their interactions, the guided mode transmission, and this is the simulation. And here they are, like that. And we're very proud of that. That's been the last 2 years. Now you can look at things like this and gain information. That's this frame magnified up. What is this? This, by the way, it's kind of flat. There's an AC Stark shift. Those are the atoms that just go by the side. So there's some that just flow by the side. What's this? I call this the Stark snake. This is atoms that are coming to the device and they ride up this blue repulsion and then they're pushed back. And what's this? These guys fall off, they're pushed back, and here they are coming back to to their more or less their free space. So this is just the Stark shift associated with the blue beam. So that's good. So you can look at it over here. You don't need the simulation and kind of figure out, but this now is quantitative comparison between these two things. I would emphasize that we're getting the information about these trajectories on timescales of kind of 100 nanoseconds and length scales of 50 nanometers. We have to know that inside of here to figure out what's going on, make this fantasy of mine a reality. I'll emphasize also that's one of the frames from the previous one. This is the measured clock spectrum. It's not so interesting. And this is a simulation. And you might not have noticed at first this thing has a dip in it. This has a dip in it. That's from Casimir-Polder. We put that in as best we know it. If you don't put it in, it's clearly different. It's different than that. So I think we're going to be able to measure, not at the accuracy we'll hear from Junier, but we're going to be able to make measurements of Casimir-Polder beyond what's been capable in atomic physics before, and address some questions that are really quite exciting in Derek Chang and another group about real Casimir-Polder potentials in the face of optical fields. Okay, finally, might it be possible to associate this clock spectrum, I've been showing you all those gaps and so on, with atomic trajectories? To know when and at what detuning an atom is in the middle. So I want to look at a measured clock spectrum and from that identify that's the place when the atom is in the middle. And I'm going to trap it by that transfer of states I described to you. Is that possible? Well, here's a bunch of, not a movie, but these are trajectories that trace through. If you blow it up, you can see they're entering and they're transiting, and a lot of them are lost on the surface. This is with TM start beam. TM has the property that in between here, it's almost flat. So there's light there, but there are no gradients. So there's no force. So all of this bending is associated with Casimir-Polder. In a trap, we wouldn't have that if we used a trap. We're just trying to learn what we can see. So if we know all the trajectories, we can calculate the clock spectrum and theoretically divide it up into everything, into the one, and most importantly, the ones that went through the center. What did they contribute? So if you take a cut there, we know this time because we're the scatter light. So at 150 microseconds, this is the total of all atoms, and that are the atoms that are going through the middle. So if we take this trapping beam that's going to transfer from one state to the other and tune it to minus 20 megahertz relative to free space and turn it on at that time here, we know that time. Boom, it's just in real time. Boom, trigger, boom, trap, boom, publish. No, trap, drink, publish. With the students who've worked very hard. So we think we have a way we haven't had before to move forward. Anyway, so that's the story. This is Alexandre Gonzalez-Tudela at Max Planck. It's just brilliant with illustration. It looks much better than the Schawlow-Townes patent, but that's the goal. Atoms trapped in dielectric structures to really put AMO physics and nanophotonics together to do my real love, the truth be known, is, good things with photons. And I've tried to indicate some of the things we could do. If you're interested, a lot of what I've talked about is reviewed, and this just came out the beginning of August with these young people who are really responsible for both the theory and the experimental advances. So thanks for your attention.
So when you trap all these atoms in 1D lattice, how do you address each atom once at a time? That seems to be, you can't do that with the guided mode, because the guided mode, the interaction will be sequential one after another.
Yeah, and they're subwavelength.
Right.
So if I could look in an image, they're subwavelength. So the first thing to do is when we use these tweezers, you put them, I'd be hallelujah if we could put 5 atoms and each one of them is 5 microns apart. And then you can image it. A lot of this physics, because we're doing it near the band edge, the block mode is pi periodic. So it really doesn't matter for a lot of the physics I described whether the atoms are 3 lattice constants or 5 or 7. The round trip phase between the atoms is the same. It matters if there's some that are 3 and some that are odd and some are even. And then the sign for the spin-spin interaction. But we'll start modestly with 1 and it doesn't matter. 2, 3, 4. But up to 5 atoms. At 10 atoms you can do things that even the guys with supercomputers and DMRG can't really follow for photon propagation. So that's in the beginning we don't have to, but we can still do good physics. In the longer term, you can put magnetic field gradients and then shift things to be addressable, say, by Raman transitions. But that'll be when you're my age.
So the second question is that, you show the state mapping infidelity to scale with 1 over n, n being the number of atoms. How do I understand it intuitively, that scaling?
Excuse me?
So in one of your slides,
Yeah.
you showed the scaling with 1 over n, the infidelity scaling. How do I understand that intuitively?
Oh, you understand that intuitively because next to the n was gamma 1d. And when these atoms are spaced at a lattice constant, they can act like a super atom, or they're super radiant. So the effective dissipation rate is n times gamma 1d. When you get rid of that other term by spacing them pi apart. So it's super radiant. And that means that if you know about these decoherence-free subspaces, for example, if you're in the right place and you need to go, and you're going to go somewhere else to make a mistake, that level now has a decay rate which is n gamma 1d. And so it's just not possible to excite it. So the n gamma 1d comes from the super radiance, and then this the protection of these decoherence-free subspaces is set by what some people call the quantum Zeno effect, that you can't get out of the space you're in.
Could you improve the localization of the atoms as they're traveling through your waveguide structure by using a higher order mode? Like a 1-0 mode or a 0-1 mode? Which would have a node in the middle.
Not really. You know, the whole game is won in the 100 nanometers surrounding the device. So the fact that we use a Gaussian, a 0, is kind of irrelevant. The whole picture, the whole story, I didn't tell you, we've used blue lattices. They're different in terms of, all these diffractive fields and what's attractive and repulsive. That they do have some advantages, but I think the laser you bring it in with is almost irrelevant. I mean, the whole thing is like 600 nanometers wide. So that doesn't really help. Is that what you meant? Whatever you put in from outside is essentially completely different by the time it's in the dielectric. The dielectric's so small. So you could use, we've talked about, for example, cesium has a 6s to 7p. That reduces the length scale almost a factor of 2. That lets you poke in a little bit. But I don't think, in terms of the external illumination and in terms of the guided modes, there are really only 2 that sit under the light line, the TM and TE I told you. So there's not a chance. Higher order modes do have more. But when you try to design devices like that, more bumps and wiggles in the block function, when you really try to fit it to an atom, those all sit above the light line for devices we know how to make, if that's what you're asking.
So early on in your talk, you were talking about atoms and waveguide, and you quoted a Rabi frequency of 10 to the 9 hertz. So if I know the transition cross-section, I know the Rabi frequency, I can work out the intensity, the light intensity, and yet, which would be relatively high for that Rabi frequency, I think. And yet you only had 10 to the minus 7 photons. So how do I reconcile not many photons and high intensity?
So I've got the atom in there. And I send in this really weak coherent state, which has a mean photon number of 10 to the minus 7. So it's a coherent state, but 10 to the minus 7 is the photon number. And when I do that, compared to sending in 10 to the minus 9 photons in a coherent state, the transmission halves. The absorption goes down. So that's this really weak case. And that's where the 10 to the minus 7 comes from. In the case where I put an atom in the excited state and look at the Rabi frequency, it's the atom makes one photon. So it's a whole photon that's causing this very large photon. There's one whole excitation. Whereas the 10 to the minus 7 is there's only 10 to the minus 7 of a photon in the field that interacts with the atom. Does that make sense?
Well, intensity is photons per unit area per unit time.
Yeah.
And 10 to the minus 7 doesn't sound like a lot of photons per unit area.
Well, that number, to be clear, That's that's relevant to the Misha Lukin's group at Harvard, is in a cavity. So that there's not per second, it's just a number inside. You can calculate an intensity that's circulating. But indeed, it's not very small. It's not very large. And that was the point of that graph I made. That when I started, it was the smallest number anybody had ever made, and even in tiny, tiny semiconductor diode lasers, was 3,000. And you go down, 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 and you can see, part of it's a ruse, let's be honest. What really matters to the atom is the electric field. But if I tell you the electric field, that's the square root of that number, and that's not as big, and I'm from Texas.
So I'd like to ask a final question before we stop for coffee. So as I listened to you all the way through, it seemed to me everything was lithography here, that you have to make perfect dielectric structures to work so well. How, are they that perfect, and how do you make them? And you sort of didn't say anything about it at all, but I would have thought this was absolutely critical part of it.
Oh, it absolutely is. And in the end, that works the best. The atoms we still can't grab, but we're fortunate at Caltech to have
You mean the alligator really works?
Oh, it works. We don't.
You can make it?
You don't really see the defects.
You don't see any.
No, if you have, we have some defects, but you know, if some of the teeth are wrong or something like that, then when you measure the band structure, you see big deviations from what you were calculating. At some level, when you get lots and lots of, you put one defect there, it can be Anderson localized. So you don't actually get light through, and you get what you might think of as a band gap because it just reflects. But that's all characteristics we've modeled, we've looked at, but then we measure. And so we're fortunate we do it. It's heroic by my students who learned to do this in the Cavalier nanoscience. So we have a big gift and well managed by Oscar Painter to keep stuff really working so we can use it. And then people like Oscar and Kerry Valhalla to talk to about, you know, how do we do this? And so it was really just, on one hand, day and night. One of those students actually is the lead author on this atom processes in the band gap. Now, how could he learn all this atomic physics and be making devices? He's one of triplets, I think. I mean, it's just a heroic effort by that group of students, and you know, I can't brag about it, but when I go and people who know about nanophotonics see these structures, they go, "It's just amazing."
Well, thank you. Let's thank Jeff once more time. Thank you very much.